All right. Hello, everyone. Welcome back to Comp 2160, the course where you do your assignments in class. I hope that you're all doing okay today. It's another windy, dreary day. It's another windy, dreary day. We have 3 classes left, including today. Tomorrow we will have 2 classes left, and then we will have 1 class left, and then we will be done the course. Except that final exam part, but we will be done the course material. Today, we are going to be taking a look at the two samples that I've given you before. One of them is search.java. This is that code that we went through and we switched the implementation of the abstract data type. So we went from array list, which was big O(n), to hash set, which was big O(1). And we're also going to be taking a look at game.c today. This is that 5th test case that I've given you for your implementation of zones. I've put both of these files on the course webpage under today's lecture, so you can just quickly find them if you want. We're going to be taking a look at these today, specifically in the context of coupling and cohesion. So I want to be trying to assess these code samples on coupling and cohesion. So you may find it helpful to have these on your screen. I'll try to keep them on my screen as much as possible, but especially with game.c, it's quite long, so you may want to have it on your own screen just to be able to take a look at it as we're going through it. So what I want you to be able to do today is, this is continuing. I want you to be able to, given an existing solution, identify and explain where the use of appropriate data structures, algorithms, and/or techniques such as caching and lookup tables provide better paths to optimization than low-level code. Today, we're actually going to kind of do the opposite of this, and we're going to be looking at a little bit more of this low-level code stuff than we are the high-level optimization like data structures and algorithms. Today, we're going to be looking specifically at how can I pack bits of data into a byte? So I have 2 examples that I want to go through where we have 1 or 2 bytes worth of space, and I want to maximize my use of 1 or 2 bytes of space, as opposed to the alternative that we're going to see. I want you continuing to be able to describe the benefits of modularity and use simple metrics to specify the degree of independence, such as coupling and cohesion. Again, today we're going to be looking at 2 code examples. So last week we looked at abstract ideas and thought about coupling and cohesion. Today I want to look at actual code and think about coupling and cohesion. And the other thing that we probably won't get to today, but I'm putting it in here for completion's sake, is I want you to be able to use function pointers to parameterize behaviors. This is something that C has had the ability to do for a very long time. This is something that Java has only been able to do in the last like 5 or 6 years. This is something that's quite new in a language like Java, which itself is fairly old, but has only begun to start showing up. We're going to take a look at this in the context of trying to emulate OO in C. We're going to do a really bad job of it, but we're going to try our best to see if we can emulate or simulate OO in C. Before we get to any of that, I asked you this question last class. What are we trading for space when we compress data? And I asked you for some feedback, and I'd like to share with you some of the feedback that I got from you. This one, I think, is a great answer here. This one says, computing power and time. We are trading computing power and time for space when we're doing compression. It's taking time to do the compression. We have to call a function to compress our data and then call another function or run a program and run another program to make our file or data smaller and then make it bigger again. We're also trading time for that. So computing power and time, I like that. Another one here, we're trading processing power for space, question mark. I'm going to firmly put that into an exclamation point. Yes, that is absolutely what we're doing. I want to point out this specific word here, power. We are trading power for space. I actually didn't really think about it this way until I started reading these. And I'm really grateful that you used that specific word, whoever wrote this and whoever wrote this one, because we are literally like consuming electricity to save space. We are running instructions. Yeah, we're calling functions and running programs to save space. And that does take time, but that also takes extra instructions. Like we have to run electricity from our power outlets through our computer, through our processor to make that data smaller. That takes power. That takes electricity to do that. I liked this one as well. Time is money / cross off space. Yes, we're trading time. And I guess indirectly money. We're paying for this power. I mean, I'm not paying for this power, but somebody's paying for that power. I liked this one. Primarily because of the nice little flowers that we had on here. But when we compress data, we trade space for quality. And I liked this one in the specific example of lossy compression. We're potentially losing quality. So if we're taking an image from a webcam or from a high-end digital SLR camera, and we're compressing it with JPEG, and you make it into a postage stamp, you're making it a lot smaller, and you're losing a lot of information, and you're potentially losing a lot of quality with that. I saw this one, and I thought it was good too. We were trading time used in extra CPU cycles. So this is getting to that low level. We're running extra instructions to perform the compression, lots of calculations, and help A3 is hard. Sad face, sad face. If you have questions about assignment 3, please feel free to come see me during my office hours. It is hard. I'm not even gonna make like light of that. It is hard. It's a challenging assignment. But like I said, when you get there, it's gonna feel so satisfying that you were able to get it to work. I do have office hours today. I have office hours again on Thursday, and the Computer Science Help Center is also open throughout the week. And I know at least today and on Friday, the person that's in there in the morning is somebody that I trust quite a lot to help with stuff like this. His name's Icaro, if you haven't been to the Help Center. And this is the last one that I'll share with you. I took this one because it was partly because it was so long. It says, if I were to compress a sandwich to save space in my lunchbox, it would save space and even flavor. I'm not sure how that would happen, but it would look like an incredibly ugly ball of mush. In the same vein, we are trading readability and clarity, question mark. The sandwich part, yeah, if you did squish it up, it would be a giant ball of mush. I mean, I guess I'm gonna say that yes, we may be trading readability and clarity, not so much. You could say that the compression algorithm that you might be implementing is quite complicated, but from our perspective of someone that's using that algorithm, we don't actually care about how it's implemented. So I'd say if we can call a function and compress our code, we're not trading that. But I liked this because of the sandwich analogy. So thank you all for giving me that feedback. And I'm going to confirm that, yeah, I think that what we're doing here is we're trading time and energy for space when we're doing compression and decompression. That's what I think the answer to that question is. Any questions about that? I think that's okay. Okay. So last class, we were talking about profiling. 2 classes ago, we were talking about profiling. Yesterday, we were talking about changing our implementation of our abstract data type, adjusting data structures to make things go a little bit faster. We talked about compression as a way to save space. And now we're going to talk a little bit about how we can manipulate bits to save some space. So getting to this little like low-level stuff as opposed to doing the higher-level things. We're going to be thinking about manipulating bits. All values that we have in our system, everything in our system is just bits. If we go all the way to the bottom, we've got pulses of electricity that are high and pulses of electricity that are low, and these are the bits that we're talking about, 1s and 0s. Any bit manipulation that we're doing should be done using unsigned variables. So each of these has this unsigned property. I've told you about this one before, and you've seen unsigned short in the form of that z size t type. But every variable type that you can have in C, except for void, actually, I don't think you can have an unsigned void type, but every variable in C can have an unsigned type that goes along with it. Unsigned types have this great effect or great feature that they can't be negative. And what that also means is that you get bigger numbers instead of smaller negative numbers. So the range of a normal number is from -2 to the 31. If we're thinking about those integer types in Java, if we're thinking about some of the types in C, it goes from negative to positive. In an unsigned type, we start at 0 and we go all the way up to 2 to the 32. So we get kind of an order of magnitude of extra values that we have from it. The other effect is that unlike regular integers where they're overflowing to the smallest possible value, unsigned integers overflow to 0. They just go back to 0 as opposed to overflowing to the smallest possible negative number. We can also use them for reliable bit manipulation. And the specific reason for this is that when you have arithmetic, when you're doing these kinds of operations on numbers, the sign that they have is not going to affect the result of the operation. I'm not going to talk any more about that. That's something that you will see in Comp 2280 when you're thinking about representing numbers using something called 1's complement and using something called 2's complement. You might have seen those before, maybe, but in Comp 2280 you will definitely see those things. What I'm going to say for us is that we are just going to use unsigned values, period, full stop. We're just not going to try and do bit manipulation with signed types. We will just always use unsigned types. We're going to use a set of operators to do this. So we're going to operate on variables using these things called bitwise logical operators. We've got an AND operator, we've got an OR operator, an XOR operator, and an OR mean approximately what they mean with Boolean logic. If you have two trues and you AND them together, you get a true. If you have a true and a false, you get a false. If you have a false and a false, you get a false. OR is the same as what you're expecting it to be. If you have a true or a true, it's true. If you have a true or a false, it's true. If you have a false or a false, it's true. XOR is exclusive OR. That means that it can be one or the other, but not both. So true XOR true is false. True XOR false is true. False XOR true is true. False XOR false is false. So it's one or the other, but not both. This tilde is a unary 1's complement. It's kind of the same thing as not, where not says change this false to a true and change this true to a false. This says take all the bits and flip them. So whatever was a 0 now becomes a 1. Whatever was a 1 now becomes a 0. Then we've got two operators here. Left shift, this moves bits over, and right shift moves bits over. Someone came to see me today, and they told me that they had not really seen binary numbers before. And I think this is a reasonable time to remind everyone, if you have seen binary numbers, what they look like, and if you haven't seen binary numbers, what they look like. So let's take a look. I'm going to show you a little table that I like to draw when I'm starting to think about working with binary numbers. I'm going to do a table that has 3 columns in it. The first column here is going to be my decimal column. The second column is going to be my hexadecimal column. And then the last column is going to be my binary column. In my decimal column, I'm going to write out the numbers that I'm kind of used to in decimal. So I'm going to start by doing 0. That's the first number that I'm thinking of. And I'm going to go all the way up to 16. to 15, sorry. I'm going to go all the way up to 15. Hexadecimal numbers start at 0 through 9. They just use the same basic set that we've got in our decimal number system. And then once we get to 10, we still use single digits to say A, B, C, D, E, F. And then when I do binary representation, we're going to be doing 4 bits for each of these values. So 1 bit is one single digit, 1 or 0. We're going to do 4 bits to represent each of these values. When I do this, I use what I like to think is a little trick, but maybe this is just something that everybody knows. I don't know. I'm going to start with the rightmost column of numbers, and I'm going to start writing a 0, and then I'm going to switch to a 1. And then in my rightmost column of numbers, I just keep switching back and forth, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and I do this 8 times. I do 8 pairs of this. So 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, and then 0, 1. So I have 8 pairs of this. In my next column, I'm going to do 2 zeros and then 2 ones, and then 2 zeros and then 2 ones. So 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. In my next column, I'm going to do 4 zeros and then 4 ones. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then in my very last column, I'm going to do 8 zeros and 8 ones. I'm going up by powers of 2. So 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. Done a really bad job of aligning these things. But I think that, that we can see the connection here. This is F and 15. This is F and 15. And then it kind of goes up from there. So when I'm drawing these numbers out, I'm doing a table that kind of looks like this to help me really quickly get this. I'm bad at doing recall for like A is 1010. I'm bad at doing that, but if I draw this table out, it helps me a little bit. Has anyone seen this table before? Yes? Okay, yes. So some of you have. Good. So good. This is a reminder if you have seen it before. If you haven't seen it, this is an introduction to this table. I'm going to go back to my slides, and then we're going to come back to doing a little bit of drawing here. So I want to take this set of operators, and what I want to be able to do with it is I want to be able to encode colors that are used by the Game Boy Advance. On the Game Boy Advance, we use exactly 15 bits to represent colors. 15 bits are going to be used, and for each of those colors, red, green, and blue, we're going to use exactly 5 bits worth of color. I'm going to not use these numbers to begin with. I'm going to use these numbers when I write some code to do this. I'm going to use numbers that fit within the 4 bits that we've got to start so that we can take a look at what these different operations are going to be doing. So I want to do this on paper first, and then I'm going to do this in code. I want to write the code to be able to do this. So I'm going to switch back to my tablet here, and I'm going to scroll up just a little bit. And what I want to do here is I want to basically encode my Game Boy Advance color. So GBA color. And what that looks like is 15 total bits. And it's going to be 0B. So when I write binary numbers, I put 0B. When I do hexadecimal numbers, I write 0x. When I do base 10 numbers, I don't write anything. I just write them as numbers. The very first bit here, it kind of doesn't matter what it is because we're going to be doing just 15 bits. But we can't get just 15 bits in our number types. We get 8 and 16. So that one extra bit is going to be just unused. We're not going to care what it is. We don't use it. We don't care what it is. The rest of the structure is that we're going to get, for blue, we will get 5 bits. So blue, 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 and then blue. I'm trying to space these out so they're each 4 bits as opposed to putting 5 bits in a row. Then we're going to do green, 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 green. And then finally, we're going to do red. So red, red, and then I haven't done enough Bs. Five blues. 5 greens, and then 5 reds. I'm going to pick some colors, like I said, that are going to have values for these numbers. These numbers are going to be within the range of 0 to 255, but I'm just going to pick numbers that fit into the table that we've got here with 4 bits. And we're going to say that the top bit here is always just going to be 0 for the numbers that we're working with. So I'm going to say that the number that I want to encode for colors here for blue is going to be C. The number that I want to encode for green is going to be 9. And the number that I want to encode for red is going to be 3. The very first thing that I need to do is I have to start with the number that I've got here. I'm going to have to take this number. I'm going to have to use an operation that's called masking. Again, we can have values that are either 8 bits or 16 bits or multiples of 8 bits, but we cannot have like just 5 bits. So I need to be able to have just a value that has C in it, but it's going to have 8 total bits. So I have to mask it. I have to turn off other bits that I don't need. And then I'm going to have to do a shift operation. I'm going to have to shift the bits over so that they are moved into the correct place in the number that I'm trying to build. So when I start with C, what I'm going to start with here is that my value for C is going to look like, I'm going to switch back to blue. C is going to be equal to an 8-bit value. And the 8-bit value that we're going to have is going to be 4 zeros, a 5th 0. C is 1100, so it's going to look like this. 9 for my green value is going to be 4 0 bits. And then it's going to be 1001. And then 3 for my red bits is going to be 0011. And my goal is to take this number set that I've got, each of these numbers, and then kind of paste them all together here so that I get this. My first operation is that I want to make sure that whatever the values that I have in these bits, the parts that are over here, these 3 bits, I don't care about them. I don't know what they, I know that there's 0 here, but I want to make sure that I'm getting just these bits as the ones that are set. I want to make sure that just the 5 bits that represent this color are the ones that are set. The way that I accomplish that is to mask the values using the AND operator, the logical, the bitwise AND operator. So I'm going to use my AND operator here. And what I want to AND this value with is the value that represents 111111000. I want to say the values that are set in this are the ones that are going to be set, and I want to make sure that these ones are all 0. So I'm going to do a bitwise AND with 0B000 and then 11111. So in hex, this is going to look like 0x1f. I'm going to do this AND operation because if I've accidentally set this value here to be a 1, if I've accidentally set that, or the value that I've got has these extra bits that are set, I don't want that to affect the result that I'm getting in this value that I'm doing these shifting operations on. So I'm going to AND this with 0x1f, and I'm going to do the same thing for each of the values that I've got here. So and then I'm just going to write 0x1f. It's going to be the same for each of these things. Once I've masked off, so I'm going to write just a little comment here. This is masking. Once I've got these values masked, then I need to use my shift operators to move these 5 bits over to this part of my 16-bit number. So I need to take bit number 0. I'm going to say that bit number 0 here is the least significant bit, and I need to shift it from this location over here. So I'm going to count. This is shifting at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I shift this value to the right by 10 places, I'm going to take these 5 bits and I'm going to move them over to this spot, and I'm going to leave a bunch of zeros behind it. So what I'm going to say here is C and 0x1f. I'm going to wrap parenthesis around this. I'm going to make this not look like an 8. And 0x1f. And I want to shift this 10 bits to the right. Left. Oh my gosh, sorry, to the left. I need to look at my hand still. I don't know if you've ever done this trick as a kid or if you were ever taught this trick as a kid. I still need to do this. I still need to do it, yes. I need to shift it to the left by 10 bits. For my green value, I want to take bit 0 here as though we're in this position, and I want to shift it to the left 1, 2, 3, 4, 5 bits. So these 5 values will each get shifted to the left by 5 bits to put it into that position. So I'm going to do this masking operation, 0x9 ampersand 0x1f, and I'm going to shift this to the left by 5 bits. And my last one here, for red, doesn't need to be shifted over at all because it's already in this least significant position. So I just need to do the masking part. I just want to turn whatever these bits are off so that I just have 5 bits left. And so for that one, I'm just going to say 0x3 ANDed with 0x1f. I've got these three values now, but I want to put them all together into one 16-bit value. And so the way that I'm going to accomplish that is to use my logical OR operator, or my bitwise OR operator. I'm going to OR each of these things together. So this operation here is going to result in 0b, I don't care, 0, 1, 1, 0, 0, and then also 12 more zeros after that. That's the first one that we've got. This operation here, shifting this by 5, is going to result in 0b, I don't care, 0, 0, 0. It's going to move to the 5th position here, so 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0. And then the last one is going to be whatever it was before, but with things masked off. So I'm going to get 0b, I don't care, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1. And when I OR all of these things together, I'm just going to go through, and any bit that's set in each of these columns is the one that I'm going to get as the output. So I kind of like doing a sum here. I'm adding them all together. Yeah.
Logical OR is the same as division, right?
Logical OR is effectively the same as division, yes. It's effectively the same as addition. It's not identical to addition, though. If I have 3 ones here and I OR them together, I will still just get 1 out. Again, you'll see a lot more about this in Comp 2280, where you'll start to think about how do you make circuits that do adding binary numbers together. But for now, for us, we can say that if one of them sets in that column, then the result is going to be set in the output. Yeah. Flipping the bits and adding 1.
They made like a circuit to add binary together. And like Gerhard gave us a trick, like flip the bits add or something. I can't remember what it was before.
Flipping the bits and adding 1, I suppose, might change the sign of a number if you're doing 2's complement. Yeah. 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 But again, you'll see more about that in Comp 2280 for sure. Yeah. Okay, so I want to take this and I want to start writing just a little bit of code to get us to having something that can do this. So I'm going to switch back to my terminal. Please feel free to follow along with me if you are interested in doing this. This is going to be a pretty short file. I'm going to copy my template from the previous directory, and I'm going to call it color.c. And I'm going to edit color.c. And I'm going to add an include here. We have previously talked about how different platforms and different types will result in different sizes for each of those different types. So an example of that is the long type on my machine and the long type on an M1 Mac have different sizes. They have different numbers of bits that represent that type. I'm going to include a new header file at the top here that's called stdint.h. stdint.h gives me access to some type-deft values that will specify how many bits are used, that I can use these specific types, and then when I compile it on these different platforms, it will just guarantee that I get those specific types. So what stdint.h is giving us is the ability to say, the ability to specify the number of bits that are used for a specific variable. In my main function, what I'm going to do is I'm going to declare 4 different variables. The first one is uint16t color, and I'm going to set that to 0. uint16t here says that it's a type, so underscore t is type. I want to have an unsigned integer that takes exactly 16 bits. That's what I'm asking here for with uint16t. I'm going to declare 3 more variables, uint8t, r, g, and b. For each of these variables, I want to have a type underscore t that is unsigned integer that takes up exactly 8 bits. In stdint.h, this might be, as an example, typedef as this is unsigned char. In stdint.h, this might be typedef as unsigned short. But we don't have to care. We don't have to care. We can just say, I want to use exactly this many bits. And when I compile it on my Linux machine or my Mac, it will be 16 bits, and I get that specific value of bits, that specific number of bits. I'm going to say here that I want R to be 21. So I'm going to go back to the colors that we were using in the example. G is equal to 0, and B is equal to 25. These are the numbers that I want to have out of 255. To do the operations that we were talking about just a second ago, what I'm going to say is that color is equal to, I'm going to take the blue value first. So blue, I'm going to mask it 0x1f, and I'm going to shift that over 10 bits. I want to make sure that when I'm doing this, I'm doing brackets and parentheses around these sub-expressions. Operator precedence for bitwise manipulation is best to be explicitly stated with parentheses. If we're doing any of these bitwise manipulations, we want to make sure that we're doing this intentionally with brackets to make sure that that precedence happens in the order that we're expecting it to. I don't even remember what the actual operator precedence is, but I think that this shift operator is lower than the AND operator. I can't remember though, and I want to make sure that I'm not doing left shift on 1F, but I'm doing left shift on the result of doing the AND here. So I'm going to say that color is equal to blue shifted over 10 spots. I want to say that color is equal to this ORed with my green value masked with 0x1f. So we get those last 5 bits shifted over 5. And then what I want to say here is just R masked with 0x1f. So I don't need to shift over those last bits to move them because they're already in the right place in this variable that's called R that has 8 bits. I'm going to print out the color is %x. I want to print this out as a hexadecimal value, and I'm going to print this out as color, and then I'm going to exit. I'm going to pop open a new terminal to the side here. I'm going to put these expressions just on different lines so that we can see them all at the same time. I'm going to make color, and I'm going to compile it and run it. The color that we get out here is 6415, 0x. 0x6415. I'm going to pop open my calculator here really quick. And there's a programming mode here. And so if I enter 6415, I'm going to enter this as hexadecimal, 6415. Then the value that we're getting here is listed right here on this bottom row. It's the first 5 bits, then the next 5 bits, then the next 5 bits that represent the colors that we've got there. Yeah. So in this case, that's a good question. The question is, what if I don't do the masking? So I'm going to write this without caps lock turned on, and then I'm going to copy this whole expression, and I'm going to paste it. And I'm just going to delete the masking parts. I'm going to make it again. Because I'm just assigning, it's just going to overwrite whatever was in there before. And I'm going to run it. And it's going to be the same. It's going to be the same because when I specify these hard-coded numbers, 21, 0, and 25, those top bits are always just going to be 0 anyway. So masking them doesn't really have any effect in this specific example. If I were to do something like setting G, I'm going to set R to be 255 here. So make it the maximum possible value. And now this is setting all the bits to 1. If I make this again and I run it, it's written into the 5 bits for the R, but then it's also started to write into the bits for green. And so green here was 0, and so those next 5 bits should all just be zeros. But now they're all 1s because all 8 bits have been stuffed in there as 1s. So if I change this back, so if I comment this part out, the value that we're going to get here is going to look a little bit different, 641F. So those last 5 bits are 1 and then 1111. And then the rest of the green is going to be the 0 that we're expecting it to be. Yeah. So that's the purpose of that, is to try to make sure that we're constraining ourselves within the range of values that are acceptable for 5 bits, which is 32, I guess. Yeah. Any other questions? Yeah. Yeah, absolutely. So the question is about adding the 0x in front of the 1f. If I just put 1f here, you'll see that the color has changed, because when we have number literals in C, they can't have letters in them. And the 0x here is explicitly saying that this is a number literal, but it's a hexadecimal number literal. So what follows after the x up until the next thing that's not a number or a letter that's up to f, that's the number literal that we're doing, but it's in hexadecimal. When I just type in 10, it knows that 10 is just a decimal number. It doesn't have to worry about it. But the 0x here says what follows is a hexadecimal number. Yeah.
So then it's like the same thing with you're doing the printf, you're doing the %x.
Yeah. When I put 0x down here, this is just me writing that because I want to see 0x in the printf. That this 0x doesn't affect anything. The %x is what prints it out as hex value. Yeah. Yeah. Any other questions? Okay, cool. So what this is accomplishing for us with the Game Boy Color is that instead of having to use 24 bits to represent colors, we can now use just a single 16-bit value to represent colors. And on a platform that's constrained in the way that Game Boy Advance is, with the hardware that it's got, it's going to work better with 16 bits or 15 bits for color, as opposed to the 24 bits or 32 bits that we might have on a desktop like this one. The other example that I want to take a look at, I'm not going to write this, is that I want to just read through this. We can do lossless compression on genetic data by packing bases into a single byte. Okay, let me introduce biology a little bit to you. So we all have genomes. We all have genomes. Genomes are kind of like the instructions that are used by our bodies to say this is what we look like. This is our genetic makeup. Bacteria have genomes. They are significantly smaller than human genomes. Our genome is about 3 billion base pairs long. Base pairs, when we're thinking about them, are going to be just the letters A, C, G, and T. That's what it is. So it's, oh my gosh. I don't even think I can remember what they are. Guanine, tyrosine, nonine. It's not niacin. I don't remember what it is. It doesn't matter. It's A, C, G, and T. These are the 4 chemicals that make up genomes. Biologists are really bad at representing data. Biologists are really bad at representing data because what they do for genetic databases is that they have just multi-gigabyte size text files. Just plain text. So you can open it up with Notepad. You can't open it with Notepad because it's too big. You can open it up with maybe Visual Studio, but it's just a plain text file that's filled with the ASCII characters A, C, G, and T. Each ASCII character takes 8 bits. It's an 8-bit value. It will always take 8 bits. And if we just have 4 possible values that we're encoding into one 8-bit value, then we're basically wasting 6 bits. We can do 4 by doing 0, 0, 0, 1, 1, 0, 1, 1. That's 4 different values. The other 6 bits of the 8 bits are effectively wasted space. They are used by the letter A, they are used by the letter C, by the letter T and the letter G, because there are bits set there, but we can transform that into just 2 bits. So I've got an example here that I'd like to just quickly take a look at that's called genome.c. I will share this with you. I've got 2 functions that I've declared, compress and decompress. And I've got 2 functions here that I've declared that will go from 2 bits and from bits. From bits takes a single character and it returns an unsigned character that just has 2 bits set. From bits takes a single character that has just 2 bits set and it returns the corresponding character to that thing. In my main function, I declare this variable that's called genome, and then I declare this other array that's called compressed. Genome here is 16 characters long. So it's taking 16 times 8 bits of space, but we can put this 16 times 8 bits of space into just 4 bits of space, 4 bytes of space to represent the same thing. I print out the original genome, and then I call this compress function. And what the compress function does is it loops through every character in the input string in the genome. It converts it to bits. So I'm going to go down here to the 2 bits function. And it just returns 1, 0, 1, 2, or 3 for each of those 4 characters that we're getting as input. And then up at the top here again in compress, what we're doing is I'm shifting over the first character, the 2 bits that I get back from that by 6, and I'm masking off just those 2 bits. I don't care what the rest of that thing is. The next one is I'm doing the next character, and then the next character, and then the next character. And in the same way that I'm shifting over those color values for the Game Boy Advance, I'm shifting over just each of these by a couple of bits. When I go through the process of decompressing this, I'm doing kind of the opposite operation. I'm shifting over by 6 bits, and then I'm masking with this constant 0x3 for each of them because I moved the 2 bits that I want to look at to the least significant bit position, and then I'm passing that whole thing to the from bits function. And then at the end of this, I'm putting a null byte at the end of my string. So when I'm doing this, I'm going through, I'm compressing this into this compressed array. I print out what those things are, and then I'm decompressing it and showing that what I'm getting back is the same. In the decompress function, the from bits is taking it and it's making it lowercase because I just want to show that we're actually getting transformed data out of this. But a lowercase a and an uppercase a are exactly the same thing in the context of what we're thinking about right now. So when I run this code, I'm going to say make genome, and I run this. I'm going to print out the genome that was originally passed in. These are the 4 bytes that I get back that represent this same string, and then I'm decompressing it, getting this back out. We don't need to grok this code right now, but I want you to see another example of bit shifting and how it could be used for something like this. So this is available for you to read, or it will be available for you to read after today's class. Any questions about this? Yeah. Can you repeat your question, please? These are the operations that you're going to use when you need to pack a bigger number of bits into a smaller place. So in the Game Boy Advance example with the color, we're taking 24 total bits of information. So each of those RGB are 8 total bits, so it's 24 bits in total, and we're trying to cram that into one 16-bit location. With this example, we're taking what takes 8 bits, this, and we're cramming it into 2 bits. So we're using 25% as much space to represent effectively the same thing. So it's less, I mean, this is used in the real world, yes, but it's more about, I've got bigger space that I'm using right now, and I want to squish it down into something smaller, or I want to move things around. We're going to see another example of this when we do actually look at the Game Boy Color, the Game Boy Advance, sorry, in that the D-pad, when you're pressing buttons on the D-pad, we're going to have to look at a specific location in memory, and then to figure out whether it's up, down, left, or right, we're going to have to shift the value over and then compare it to some like well-known set of values that we have. But we'll talk about that later. We will talk about that later. Yeah. Okay. All right. So I will let you read this on your own time. What I'd like to do now is I'm going to skip this. I'm not going to talk about bit fields. I'm not going to talk about bit fields at all. We can just strike this from the course. This is not part of the course. You can read these notes if you want, but I'm not going to assess you on the use of bit fields in any way, shape, or form. I want to take a look at this. I want to do coupling and cohesion right now. I want to take a look at 2 code samples. The 2 code samples that we're looking at are search.java and game.c. The questions that I'm going to ask you are, how cohesive is this one code sample? So quickly to remind you, this idea of cohesion is how much do each part of this code, how much is it interrelated? How much does this thing do one thing and do that one thing well? A very highly cohesive piece of code does one thing very well. A very low cohesion piece of code does many things, and it may do those things well, but it's doing many different things. I'm also going to ask you the question, is this tightly or highly coupled, or loosely or lowly coupled? And then specifically with what? So we talked about this idea of coupling, where coupling is, how much does this depend on the implementation details of this other thing? How much do I need to know about the implementation of details of this? If something is tightly coupled, it knows a lot about the internal implementation and it relies on that implementation. If something is loosely coupled, it doesn't know much about how it works, but it can ask it to do things. I'm going to show you code samples, and I'm going to ask you this question. Tell me if it's high or low coupling, and then specifically with what? What is it tightly coupled with? What is it loosely coupled with? Cohesive is just with this code sample by itself. Is it cohesive? Yes or no. With coupling, is it high coupling or low coupling, and with specific other things that we might be depending upon. Let's take a look at search.java first. So here's search.java again. Again, this is on the course webpage, so please download this if you don't have it on your machine right now. But we are declaring a couple of collections. We're assigning them instances of array list. This was the original version that we had. We are loading a dictionary into this dictionary collection, and then we are searching through the dictionary to find something. I'm going to pop this code over to the side. I'm going to try to put as much of this on the screen as I can, and then I'm going to also open up my Mentimeter here. The first question that I'm asking you here is, I'm going to make this bigger for now. The first question I'm asking you right now is, agree or disagree? Search.java is highly cohesive. I'm going to give you like a minute or so to quickly read through the code and then agree or disagree to this question. We're talking about search.java in this one. Okay, I'll give you like 10 more seconds. All right, okay. So our statement meter here is kind of trending towards strongly agree, and it's slowly moving towards strongly disagree. I'm going to say that search.java, I am going to say that I think that search.java is not super cohesive. It's doing two different things. There are two completely separate operations here. The very first operation that I see when I'm looking at search.java right now is that my main method is responsible for reading a file to populate a dictionary. This is one operation. This is one independent operation. The other thing that this is responsible for is searching for a collection of words in the dictionary. When I'm thinking about cohesion, I'm thinking about these responsibilities, and I'm also thinking about these verbs, reading and searching. And if you think way back to Comp 1010 and Comp 1020, these verbs are often good indicators for this is a method. This might be a method by itself. This might be a good method name. Read or load file, and then search for collection of words in the dictionary. So to me, this is not a super highly cohesive piece of code because it's doing two very different things from each other. Does that make sense to everyone? Yeah. In this case, cohesiveness doesn't have much to do with I'm depending on the specific implementation of how the search is being done here. Because I'm not doing the searching. The container is doing the searching for me. I am searching for stuff, but I'm not really caring how that searching is being done. Yeah. You can increase cohesiveness, yes, by separating these into two different classes. One is a dictionary loader that returns a dictionary, and one is a dictionary searcher that searches through the dictionary that's been returned by some other thing. It might even be as simple as saying, I'm going to put these into two different functions or two different methods within this thing. Our main method here itself is not cohesive. If I separate that out into two separate operations that are two different methods, then each of those methods becomes more cohesive. The class is still not cohesive. If I separate those into different classes, then each independent class is going to be cohesive in itself. It does one thing and it does that one thing well. Is that okay with everyone? Okay. Here's my next question for you. What is search.java coupled with? So these are high-level ideas. What is it coupled with? We have a bunch of code in search.java. What does it depend on? And is that dependence on that other thing high? Does it have to know about how it works? Or is it low? Does it not care much about how it works? So is there tight coupling? It really needs to know about how this thing works, or low or loose coupling. It doesn't need to know much or care much about how it works. When you're providing an answer, please put it in the form of, this is the thing that I'm depending on, the coupled thing, and then in parentheses put high or low, or tight or loose. I'll give you about 20 more seconds. Okay, so a lot of people are writing dictionary, dictionary, dictionary. We've got kind of conflicting things here, loose and high. Dictionary coupled with ADT and data structures and low. Dictionary, dictionary, dictionary being implemented in some sort of collection. So I'm going to point at these two, and I'm going to say that they are saying approximately the same thing. And this one, ADT, array list hash set, loosely coupled with a list of the words, and the dictionary accompanied search block high coupling. I'm going to look at these ones right here. Coupled with ADT and data structures, low. Dictionary being implemented in some sort of collection, low. ADT, low. I'm going to agree with that very strongly. We're declaring these variables of type collection. Collection in Java is an interface that specifies operations. You can add things to this, you can remove things from this, you can search for things from this, and you can iterate over it. Those are all the operations that it gives you. It doesn't tell you how the search is being done. It doesn't tell you anything about how adding is being done. It doesn't tell you anything about how removing things is being done. When we actually do the search down here in dictionary.contains, I was able to switch out array list to hash set, and it still just worked. The functionality was the same. The coupling between the specific implementation of my dictionary data type, the specific implementation of my collection data type, is extremely low here. I do not care how this works. I don't care how this works internally. It worked when it was a linear search. It looked when it was a hash table. It worked. That's all that I cared about. So I am loosely coupled here with the specific implementation of an ADT. I have an ADT, that's what I'm using. I don't care how it's implemented. I'm going to pop up here, and this one is something that we didn't notice. That's okay. I'm going to say that this is very tightly coupled with a dictionary being a list of words in a file that are separated by new lines. This code depends heavily on that. This use of scanner and the way that I'm adding things to my dictionary is extremely tightly coupled with this. I cannot change the file here with something else. If I wanted to use a file that had 2 words on each line, it's going to mess everything up. If I want to change this to use something that's not a file, like a website, it's going to mess everything up. I cannot trivially change this code that's here to work with things other than a file that has a list of words, 1 per line. So there's some very tight coupling here between this method, my main method, and the use of this specific file with scanner. If we do what you're talking about, take this chunk of code and move it into another class, dictionary loader. If this code depends on just dictionary loader, then this code does not have to care about how we load the dictionary. The dictionary loader implementation may rely specifically on that, and that's where tight coupling is okay. We have to have this sometimes, but this code would no longer care about how the dictionary gets loaded. It's just that there is a collection that's filled with strings. That's what we're caring about here. Is that okay with everyone? Okay. All right. I'm going to move now to game.c. Game.c is, you can find that on the course webpage. I'm going to pop it open here. Assignment 3, tests, test 5. Here's game.c. I can't even begin to show this whole thing on my screen. I'm going to pop this open, and I'm going to scroll kind of slowly through it. And what I'm going to tell you is that I'm asking you the exact same questions here. How cohesive is this? And then coupling low and tight with specific things. I'm going to go through some of these functions, and I will describe to you at a high level what they do. This function here that's called handle inputs, I'm going to go to the implementations of them as opposed to looking at that. Here's my main function. My main function initializes my game state. It calls some ncurses functions to initialize the screen and then make sure that I can use arrow keys, and then don't print arrows when it's doing it. So this no echo says don't reprint the arrow keys when you're getting them as input. And then my main loop here does the main loop of the game. So it displays the room, it handles input, and then we pick up items, and then we destroy zone, we clean up at the end, and we release things. Then we call this ncurses specific thing called endWin. Validate player and validate room are 2 private implementations here that are invariants for my 2 data structures. So I've got a player data structure and I've got a room data structure. Handle input calls validate player and validate room, and then it calls ncurses specific functions for getting input from the keyboard. So I want to ask, is this key up? Is this key down? Is this key left? Or is this key right? When I'm doing things with key up, key down, key left, key right, I'm changing the state of my player and then possibly destroying and reinitializing the room that we're in right now. My initialize game function takes some input on the keyboard. It copies a name. It initializes the room. It calls my invariants. Destroys room just destroys the zone. So we have a reference to my zone type here. Initialize room initializes items, and it initializes an entire room. The room is hard-coded to be 20 by 20, and then we've got items that we're adding to this room, and we're doing a zalloc for each of those. My display room function calls some specific ncurses functions to put cursors on the screen and to print characters out on the screen. My item at function inspects the state of the room itself to ask if an item is at that thing. Pick up items inspects the state of the room, and it changes the state of the player by increasing score if there's an item at that location. I'm going to go back to my Mentimeter here. I'm going to move to the next slide. And I'm going to ask you to give me an answer to this question. Game.c is highly cohesive. Agree or disagree? So as we're starting here, we started at strongly agree, and we are very quickly moving towards strongly disagree. I'll give you 5 more seconds. Okay. To me, this file in its entirety is not super cohesive. It is declaring structures of types that we have in this system. It is handling input from the keyboard that really doesn't have anything to do with the game itself, the gameplay itself. It's displaying the room. It's responsible for printing output to the screen. It's responsible for picking up items. That function has everything to do with gameplay, and that makes sense to be there. Handling input and displaying the room are kind of 2 very different things from the concept of the state of the game that we're working with. Pick up items, validate player, validate room. These are all fairly cohesive things to me. They belong in here because they are part of the game itself. Initialize game, initialize room, destroy room. Item at, these are all functions that kind of fit into this thing to me as one cohesive unit. Very specifically, the functions get input and display room, handle input and display room. This kind of changes that cohesion question to me. These no longer cohesive because it's doing these other things that aren't really related to the gameplay part of this. I'm going to move back to Mentimeter. And I'm going to go to this next question immediately. In terms of coupling, what is game.c coupled with? And does it have higher tight coupling or low or loose coupling with that thing? Giga high. Okay, I'll give you 10 more seconds for this. Okay. I'm going to take a look at curses, 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 player input. I'm going to call this curses. High coupling, giga high, high, and high. This is super tightly coupled with curses. I cannot right now change the way that input works in this code without like completely re-implementing that part of my code. This is very tightly coupled with curses right now. X and Y position, this is a reasonable thing to say, X and Y position. And it is highly coupled with that. But in this case, that's okay. That's okay. Our room is a grid. Internally in my mind, this structure is a grid, and it makes sense that we would have X and Y positions there. So high coupling with X and Y, that's true, but that's not a bad thing for me. That's not a bad thing. Tightly coupled with curses, 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 that part is kind of bad, because if I wanted to, as an example, and I'm not going to waste my time doing this, but if I wanted to port this to the Game Boy Advance, I can't in the state that it's in right now, because I'm super tightly coupled with curses as an implementation. I'm definitely not going to waste 4 hours tonight trying to do that. I'm definitely not going to do that. I'm probably not going to do that. The player in the room, tight and high. And again, that's true, but I'm going to say that that's okay. That's okay to have this tight coupling with the player in the room because that is the core game state for this thing. Going back to your suggestion, let's take stuff out and put it into its own file. If I were to change this, I'm going to use a new word here. If I were to refactor this code, refactoring means, I don't know what factoring is, but it's doing that again. If I were to refactor this code, it would mean I want to take this function structure that I've got and I want to change it. If I were to do this, I would take both of these functions out of this implementation. I would take these both out and I would put them in their own library. The library would probably be called something like game-curses.c. If I were to refactor this code, I would probably take this function, main, and move it into its own file called main.c, where game is only responsible for having the functions that change the internal state of the room and of the player by itself. If I were to remove those things, then this implementation of my game does not rely tightly on curses. The other one that I see here is zone.h and zone.h. It is coupled with zones, but I'm going to say that the coupling here is low. I don't care about how zones is implemented. I just know that I have this ADT called zones, and I can ask it to destroy itself, and it will destroy itself. I will reclaim all the memory that I've allocated in that by destroying this thing. All right, so that's where we're going to stop today. At this point, you should be able to, given an existing solution, identify and explain where the use of appropriate data structures, algorithms, and techniques such as caching and lookup tables provide better paths to optimization than low-level code. I'm thinking about this in a variety of ways now. I'm thinking about things like changing data structures. I'm thinking about things like compression techniques, and I'm thinking about things like low-level bit manipulation. You can describe the benefits of modularity and use simple metrics to specify the degree of independence, such as coupling and cohesion. So given code examples, you should be able to tell me some things about whether something is high coupling, low coupling, or high cohesion, low cohesion. I should be able to give you on a printed sheet of paper a piece of code and then ask you questions about whether it is highly coupled or lowly coupled and what it is highly coupled and lowly coupled with. I should be able to ask you if there's high cohesion or low cohesion. And you might be seeing some printed pieces of paper next week sometime. So that might be something to think about. We have not been able to use function pointers to parameterize behaviors. So we will get to that tomorrow. That's it for today's class. Thank you all for giving me a couple of extra minutes of your time, and I will see you tomorrow. Bye, everyone.